So, weak visibility polygons, yes. So, recall it is a polygon that is visible from an edge. So, here the whole polygon is visible from UV, yes. Anything here can be seen from some point, yes. This is a weak, yeah, right, yes. So, yeah. So, suppose this has n vertices, I will now prove that for a weak conflict free coloring, this polygon requires only yes, okay. So, right, let us have a bigger example. Let us look at each vertex here. Yep. So, the last, so this is UV, and we for each vertex we want the last point of UV that is seen by that vertex. So, for this it will be what? It will be V itself. For this also V itself. Let us make this more interesting actually. Yes. For this vertex here, this here acts as a blocker, and this is the last point. So, let's call this P1, P2, P3. So, this is the last point on UV that P3 sees. Likewise, we compute these last points, yes, so on. So, there are at most n such last points on UV, yes. So, let these points be here, 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 here. Now, if we put guards on these points, then the whole polygon will be guarded, right. But there is a question of unique colors, yes. If we put same colored guards, then there is no question of unique guards. So, we'll have to put guards on these points cleverly. So, for this we will use a sequence that is known in number theory as the ruler sequence. Yes, sequence looks like this. First we start with 1, yes, then so element 1 or color 1, color 2, then we repeat the sequence in front of 2, that is 1. Now, we add a unique color 3 and repeat what is in front of 3, 1 2 1, right. Again add a unique color and repeat this whole sequence, yes. So, now if the length of the sequence is n, how many colors have we used? Log of n. And then there is the property of this sequence is that let us look at any consecutive, some few consecutive colors, say this, yes, this has a unique color 4. Let us look at this has 2, let us take this has 3. So, if you take any k number of consecutive elements from this sequence, it will have a unique element always, yes. So, now guess what we will do here? We will just put this, right, we will just put this sequence in the so called last points, so on. So, this gives us a log n upper bound.
Wait, what is last
Last point is the last point. So, take any point here, any vertex here, yeah, pi say, and the last point on UV that is seen by pi is called the last point of pi.
That means you are basically doing a grid from left to right.
Yes. Yep.
Till as long as that vertex is visible.
Right. And all the guards here seen by any pi, any vertex pi will correspond to a like subsequence of the ruler sequence. So, it will have a unique element, a unique color.
Others may repeat, but one unique color.
One unique color will be always be there. So, yeah. So,
Okay, don't bother, sir.
at least. So, because here if you take this 2, 1, 3, all colors are unique. Yeah. So, we do this, we have an upper bound for weak visibility polygons, but no, the upper bound is actually for simple polygons. Yeah. So, what is done after this is, so consider any simple polygon. Yes. We will decompose this into weak visibility polygons simply. So, take any edge as a start, say consider this as UV. Now, compute the weak visibility polygon of UV, right?
That means all set of points that can be visible from some point on UV.
Yes.
Repetition of definition is required.
Okay, and so this goes like this, and like this. So I'll just shade it. For UV, the weak visibility polygon looks so. This is our weak visibility polygon for UV. So, for weak visibility polygons, we have order log n upper bound. If the total number of vertices is n, obviously for this also we will have order n. Yes. Then we don't stop here. So, look at the constructed edges here. I will take this as my next weak visibility edge. I will compute again the weak visibility polygon for this, right? Here it, and here it completes. Yes. But then if I again apply a log n upper bound, I mean that's problematic, right? Because you don't know how many weak visibility polygons will be there. Yes. But
so first one is log n1. N1 is the number of vertices.
Okay. So log
N is the total.
Yes, log n1. Then you have log n2, log n3. So if this is like root n and there are root n polygons, then it does not conserve the upper bound. But notice that say this weak visibility polygon and this weak visibility polygon do not see each other. Yes, they cannot, because since already these are, I mean everything that is seen by UV is taken in some other weak visibility polygon. Yes, exactly. So this, so we can say that we have used a set of colors here, right? C1, which has actually thrice. There is another issue which I will not go into, but we can repeat 3 color sets judiciously.
Color set.
3 color sets. Yeah.
One is red, blue, yellow, another is green, pink, like that. That's all it is, disjoint set of colors.
Yes. So this gives a log n upper bound for all simple polygons.
Log of n1 and then
Yes. Yes.
still we can say order log, thanks to order.
Yep. But see, this is the version where we are having point guards. Yes, this upper bound is for the general question. Yes, yes, yes. So, just one last statement. These things go very differently when you restrict the guards to vertices, and so this I am not going to talk about. Maybe during the collaboration. So, yes.